talk a little bit about SPI. So there's a lecture, and I always rewatch the lectures before I want to talk on it to see what they skipped, because they made their lectures based on my lectures and a little bit of more research that they did. And so there's some things they leave out. So I want to go through my lecture, which is posted, but I'm going to skip through things just to get to the key parts that I think they may have missed. Well, first, I'm going to do some examples today, demos today. And these examples, they're not online, but the video will be once it's posted, once I get it uploaded. Okay, so why do we have SPI? Because, well, with asynchronous serial, you see there's some overhead, right? You had the quiz, there's overhead. Every time you want to send, let's say, 8 bits of data, it takes an extra start and stop bit, at least, maybe a parity bit as well. And so that's 10 bit times if we have 1 start and 1 stop for only 8 bits of data. So we're losing, depending on how you calculate it, 25%, wasting 25% of the time, or 20%, whichever way you look at it. Okay, and so we want to get rid of that. Now, the good thing about asynchronous communication is you only need 1 wire for transmitter, 1 for receiver, and then a ground, 3 wires. Now, for synchronous serial communication, SPI, it requires another wire. It requires now a clock signal. And if you're a master, that's it. You don't need anything more. If you're a slave, you may have a slave select, but really it's just 1 more wire, a clock. And by having this clock, though, we now can synchronize our signals. We don't need a start bit and stop bit. We know exactly when the data bit should be sampled, either coming in or going out. Okay. Now, something also different in a SPI system, we have something known as a master and a slave, which we didn't have in asynchronous communication. They were equal footing. But here now, the master controls the action. And if somebody can think of some great words that I can use to stop calling it master and slave, I'd love it. But, you know, in connectors, you know, female-male connectors, there's plug and socket now. Parent-child, parent-child, that would work, parent-child. Maybe I'll try to convert my notes. But what the problem is if the literature still calls it master-slave, you might get confused. So, but at least in my notes, one time I'll say master and slave and never again. Parent-child, I like that. Leader-follower. Leader-follower would work too. Anyway, okay. Now, some children might get upset that I call the parent in charge. Right? Okay, so anyway, there's a master, and the master basically is controlling the action. The master initiates all the action. And it could be that all the slave does is receive data, and it could be that all the master does is receive data. You can have data in both directions, which is available, but it could also be single direction, and we'll look at examples of each. So this is just 2 devices talking through a slave system. And so this thing called MOSI master output, that same wire on the slave side, this is their slave and this is a master, it's MOSI to MOSI, MISO to MISO. But the clock, the serial clock, is from the master. That's what triggers everything. Now, there is a slave select pin that all masters have, because what if you wanted multiple masters? Then you would tell one of the masters would take charge and make the other masters slaves. But typically, most systems have a single master. And if there's a single master, then we can make the slave select pin, make it an output. Make it an output, and there's no worries about it ever going low. Because if this pin is an input and it ever goes low, it basically freezes everything, because the master is now being told you're no longer the master. So remember, all pins by default are low. All pins by default are inputs. And so if there's an input pin that you're not using, remember, when something gets nearby, it can make it go low. It could make it go high if it's not being forced to be any particular value. So if you're going to leave this guy an input, if that's an input, then what you typically do is you would put a pull-up resistor on it. So if this is an input, you put a pull-up resistor on it. So if there's nothing else connected to it, it's high. And if something else is connected to it, it can bring it down to low. So, but
Shorts?
go ahead.
Yeah, I had a question about the slave select with the low thing. Because I was looking at the video for like the control register for the SPI. There was like a bit field where there was like a master where you can like decide whether it's a master or a slave. So like does it still happen? Like
if you set it for a master, you still have the slave select pin. But you can, if it's a master, you can make the pin direction output.
Okay.
And that's the safest thing. Make it an output. Even if you don't use the output, make it an output, and then it can never cause any problems. Okay. But then you've also got an output pin that you might otherwise not have had. So if you ever need it, you got an output. And that output can be used to connect to the slave of your slave's slave select if you wanted it. Okay. It can also be used for general purpose output. Okay, so if I connect these guys up and I say the master is going to start with this data and the slave is going to start with this data. Now, how does the whole process start? Well, it starts by writing some data to the data register of the master. Well, as soon as I do that, the clock is going to start clocking, and the data is going to get, basically the master's data is going to go to the slave, and the slave data is going to go to the master, all at the same time. And but it all starts with writing to the data register for the master. Okay, some block diagrams that show a little bit more detail than the block diagrams in your manuals. There's always some a data register. There's some logic, control logic. There's a couple different control registers. This is not our processor again. And then this is the status register. Our processor only has 2 status bits. This one has mode fault. That's when you're telling it it's a master, but the slave select pin went low. I don't think we have that capability. Then there's the flag that says, okay, the SPI is finished sending 8 bits. And then this is write collision. That's when data comes in that you haven't taken out before new data is overwriting it. Again, we don't have, ours is a little different. This is how you can set the speed. It's much easier to set the speed for SPI than asynchronous serial because there's less choices. Anyway, this is kind of the picture. There's, again, 4 pins in general. This is our manual's information. It's equivalent block diagram, which is not much in there. And so it shows 2 shift registers. There's the master and the slave has a shift register. In fact, you can think of it as 2 shift registers, one for transmit, one for receive, just like we had for asynchronous serial communication. But in fact, because the way this works, you can really just think of it as 1 shift register that the information that you're trying to transmit, you stick in that shift register, it'll start going out. And when the 8-bit times are done, that same register will now have the slave information or the information that was received. So in any case, you can think of it as 2 registers, but it could also be done with a single shift register. Okay, so again, master initiates, lots of words here that they went over last night and or whenever you watch that video. So these are the registers we have to deal with, the configuration registers for the SPI. Lots of words here, lots of words, these words. Okay, so the phase and polarity, which is what Motorola called it. Motorola, I think, started this SPI. Anyway, the phase and polarity just gives every possible choice for which edge should sample a signal and what should be the default value of the clock pin when there is nothing happening. And so, because you want to sample on a rising or falling edge and you want a high or low default value, if the clock isn't clocking, there's four choices. And so they call those things that allow you to choose those phase and polarity. And so these are 2 tables in the manuals, and I think Wes went over this well enough. But here we can see mode 0 here, rising edge is when the signal is sampled. Mode 3, oops. Mode 2, falling edge, is when it's sampled. But then what's the default value? Mode 0's default value is low, and mode 2's default value is high. And then here's mode 1 and 3. And so here again, we have an edge, a falling and a rising edge, and a low and a high default value. Okay. This is that control register that Mark was talking about. So this is to give us, well, really, these 3 bits give us 8 different speeds. And that they separated one out and call it a clock 2 times, or it's not really relevant. These are the speeds that we can go, and that is a divider from the system clock. So if we're running 2 megahertz system clock, we could be as fast as 1 megabit per second, and as slow as, well, 2 megahertz divided by 128 inverted bits per second. Enable, you need this to turn on the SPI system. DORD, that's data order, least significant or most significant. And remember that asynchronous serial is always least significant bit first, but SPI, you have a choice. And the default is most significant bit first. A 1 makes it least. And then the master bit, you decide if it's a master or slave. And the mode, again, is that phase and polarity.
Great. So just to like clarify, so even if you put like a 1 in bit 4 and slave select line goes to low, it will still override it?
If it's set as an input, it'll override it. It'll be basically, it won't work. It's a master that is told to be a slave, and so nothing, any code that you wrote for it isn't going to work right. It's not going to operate. Okay. Okay, control. Then there's the interrupt control, which is just like every other system we've looked at with interrupts. This system, each of the ports, port C, D, E, and F, same ports that did asynchronous serial communication, has one SPI. And so there's one thing that says, do you want to have an interrupt? And a 0, 0, so no interrupts, 0, 1, low level, 1, 0, medium level, 1, 1, high level. This is exactly what it's always been. IF, that's the flag bit. When the SPI has completed a transmission of a frame. Right collision, okay, that's the same right collision we had in that other block diagram I showed you. Data comes in, and before you get a chance to read that data, new data overwrites it. So that's the status register. So pretty simple registers, and then the data register itself is really 2 registers with the same address. One you write to for transmit, and the other you read from for the data that's received, the inputs. Okay, so only 4 registers associated with this system. Much easier system to use than the UART, but now we're going to tie to this an external part in your lab that's called an IMU, Inertial Measurement Unit. And this IMU, it's a big data sheet, and there'll be several pages that you'll need to read that are specified, and more that you want to at least skim that is specified in the lab document. Okay, so lots of words here, skip the words. So here is I'm going to actually solve, I'm going to do an example later today in class after we finish through these notes, but this is kind of a block diagram of that. What I would do, I could do is I could use 2 micropads if I had them at home, and I'd have them communicate together. And the thing you got to know, if one's a master and one's a slave, they have to have most of the same configurations. They have to both go, for instance, most significant or least significant. The speed you don't care about on the slave. The speed is designated by the master because that's the clock. Whatever, you know, that's what we have to do. But since I didn't have 2 micropads, what I decided to do is use port C as a master and port D on the same micropad as a slave. So if I was actually going to run code, which I'm not going to run code, I'm going to show you the code, but for reasons I'll explain, I'm not going to actually run it. I would just take the MOSI from port C and run it into the MOSI in port D, and the MISO port C, the MISO port D, and the clock to the clock. SPO and copy. Okay, I don't know what those stand for though. If you can't remember what things stand for, then it's probably not a good replacement.
They're just using it as like a suggestion for like instead of using master and slave, they're
Yeah, I know, but what does SPO and SOPI stand for? You know, controller in, peripheral out. Yeah, okay. I prefer the parent-child or the, what was it? What was the other one somebody said? Parent-child and whatever. Okay. So anyway, we're going to go through these a little bit later, and so we'll set the master slave to be an output. Where so with some peripherals, you can make the slave select always true. For the XMEG itself, you can make the slave select always true if there's only one slave. But the IMU that we're using, you can't actually do that because you need the slave select to give some kind of synchronization signal at the right time. But in any case, this case, that's what we're going to do. And I'm going to do, looks like 5 different examples with this. Okay, so you want to set these things up in general. You're going to set them up, the data direction of the master, these are outputs. Slave select, you could put that in output, it'd be a good, that's an input, and it's exactly the reverse for the slave. For the control, you got to set the speed on the master, and there's no speed here. The mode, the phase and polarity got to be the same. Master's got a 1 in the master bit, and slave's got a 0. And they both have to be enabled. Okay, and it could be that in the master you have polling and in the slave you have interrupts or vice versa, but probably in both of them you at least have to deal with the interrupt control, which is spelled wrong. Interrupt control register. And then if you're going to have interrupts, then you got to deal with the PMIC. And if you're going to have interrupts, you also need to deal with the I bit. Okay, here what I've shown is a way to have a master with multiple slaves. In this case, 2 slaves. And let's see, what do I got here? So if you have 2 slaves, then you need to somehow designate the slave select. Now, anybody think of a way to only use 1 pin to choose a slave?
maybe inverter.
Yeah, use an inverter. So if I have 1 pin, then I could just use an inverter. Let's say this 1 pin goes to both places, and I just put an inverter in one. And then if it's high, one of the slaves is selected, low, the other selected. So here's a way to do 2. Now, if you can do an inverter to make 2, I could use, how do I do 4? And I think they mentioned this in the video last night. What if I had 4 slaves? How can I deal with 4 slaves without using 4 pins? Part you learned in 3701.
On decoder.
Right, decoder, 2 to 4 decoder. Okay, but anyway, this is the setup of doing this. Now, you can't have 2 slave outputs. Both these slave outputs can't be true at the same time. If they're true at the same time, boom, which is why you had the slave select. Okay, and so I show this. This is the data register and the flag bit. Those are the things you always have to deal with in a master, in an SPI system. Okay, so here, this is something that's not in the lecture, and that's why I wanted to specifically discuss this. This is how do you use the SPI system to make more ports? Because sometimes there are a lot of processors that do not have an EBI, an external bus interface. And so what do you do if you run out of ports? Well, you can use SPI to make as many more ports as you want. And so what I'm showing here is a way to make not an 8-bit port, but a 16-bit port. And you could think of this as 2 8-bit ports, but it's really a 16-bit port. And to do that, I'm going to use some shift registers. Any kind of serial communication is involved with shift registers. So I use 2 8-bit shift registers. These are both 595 shift registers, which I don't remember. It's only because it's on this page do I remember the number of the chip. But these shift registers have actually 2 clocks. One, it's called the latch clock, that takes the data that's inside and copies it to the outside. And then there's the other, the shift clock, that takes one bit as it comes in and sticks it in the shift register. First bit, new bit comes in, second bit, third bit, right? So the shift clock lets the bits come in one bit at a time, and the latch clock takes all the shifted in inputs and then just copies them all at the same time to the outputs. So that's what we need. So this case, I'm making two output ports, or one 16-bit output port with any or any systems SPI system. In this case, we're kind of think of it as our microprocessor, but could be another microprocessor or another SPI system. So anyway, we have see the process here. So first, you got to get the right phase and polarity to deal with the edges. So this clock, there's a rising edge here. So you need to make sure that the data is available on rising edges. So that sets at least, I think it's called the phase. It sets one of those two parameters. So maybe two different ones will work because there's nothing that really says what the default value has to be for the clock with this design. But then here I've got this GPIO here that's going to say to transfer the data. This guy right here is when this clock happens, the data that's inside both of these should go out to the outputs. Okay, so let's start the process. So you got some data you want to send out. So you send it to the, once the SPI is set up, you send it to the data register. You send it to the data register, it's going to start going out one bit at a time. And when it goes out, the clock is going to occur. And so each of those first 8 bits will end up 1, 2, 3, 4, 5, 6, 7, 8. But I told you again, this is supposed to be a 16-bit register, a 16-bit output port. So then you store another byte to SPI. Well, what I've got here is the serial output here goes to the serial input of the other. So when we get 8 more clock edges, the bits that were here will end up here, and the new bits will then fill up this first shift register. So at the end of 2 SPI cycles, we've got 8 bits in here, and we got 8 bits in here. The first 8 are now in here, and the second 8 are here. And then we just cycle this pin right here, make it go rising edge. Give it a rising edge, and at that point, these values will come out here, and these values will come out here. And we call this a 16-bit port because all the outputs change at exactly the same time at this clock edge. So it's a 16-bit port. But if you can make a 16-bit, you can make a 32-bit or a 128-bit or whatever you want by just having more shift registers. But of course, we can just get rid of one of these and we have an 8-bit port. So very common if you need to add a port to use SPI. Very common. And we can do this with inputs or output ports. How do we know when to set transfer? Well, when the SPI is done, when the SPI flag is true, that says the SPI is done sending the byte, and if you're trying to send 2 bytes, after the second one is done, then under program code, you make that rising edge. Cool? Okay, so that's 2 output ports, or a 16-bit output port. Now let's do input ports. So this is a different shift register, 165, and here I've got parallel inputs. And so I've got 2 different clocks here. I've got parallel load, and what parallel load is going to do is going to read these pins and stick them inside. In fact, these will be read at the same time because the parallel loads are tied together. And that comes from this GPIO, like the last one. So first thing we're going to do is make a rising edge there and copy all the inputs, 16 inputs all at the same time inside these 2 shift registers. And then again, we've got to set the SPI system to phase and polarity to give rising edge when the data is available, when the data is going to be read. So we're going to set it up very similar to the last one as far as phase and polarity and master and all that. And then what we're going to do is we got to start the process. Well, notice there's nothing connected to MOSI. Doesn't matter. The way you start a serial communication is you write data to the master's data register. So you can write your favorite number, any garbage number you want, or 37, You can write anything to the data register. Doesn't matter what it is. No one's going to see it. It goes off into the air. But that will trigger the clock to start happening. When the clock starts happening, first thing that's going to happen is one of the bits in this is going to go out. And then when that happens, one of the bits here is going to be shifted here to take its place. And so this is going to happen 8 times. At the end of those 8 cycles, all the bits that were originally here are now inside the processor. And all the bits that were originally here are inside this shift 1 register, shift register 1. So then you're going to read the value in the data register in the SPI, save it somewhere, then write some more garbage to the SPI data register. That's going to start the second set of shifts, and then the second byte will appear here too. Store that. Now you got all 16 bits. 16-bit input port. Okay. Is it preferable? Okay, so what's the drawbacks and the advantages to SPI? Well, what's the drawback? Anybody see any problem with this? Let's just assume there was one. What's the disadvantage of doing this?
It takes 8 clock cycles.
Takes 8 clock cycles. It's ridiculously slower. Now, SPI is fast, maybe 1 megahertz, if a 2 megahertz clock, but that's still probably at least 8 or 16 times slower than parallel. What's the advantage? Well, you may not have a choice. You may not have EBI. And the other advantage is you only need 3 pins. Or 4 if you count. Well, 3 pins. So that's instead of 8 pins at minimum. Right? Minimum is the data bus. Now, those aren't additional pins because if you have a data bus, the data bus can be used in 100 different places. And you need all that address decoding. Here, you really just need 1 pin. And even if you have 6 of these, you only need 1 pin. Okay, so SPI, it's preferable if that's no other choice, which is quite often. Probably half the processors out there, half the microcontrollers out there, maybe even more every day, don't have a bus. They don't have data and address bus and control bus. They don't come out. They're internal. They don't come out. And they do this because they say, what more do you need? I'm a microcontroller. I got every piece of memory you need. I got timers. I got serial capability. I got everything you need because you know what? SPI, what if your microprocessor didn't have SPI? You know what? We can use EBI and an SPI chip. In fact, that's what we used to do in this course. Well, we didn't do with SPI, but for the UART, we actually had labs back in the olden days when we had 13, 14 labs a semester. We did the internal serial communication asynchronous, and then we had an external chip. I thought the number flashed in my head, the part number, whatever. We use an external serial port as well, using EBI external bus to control it. And there are external UART chips that have 4 or 8 ports right on it, 4 or 8 serial ports built into it. And they're very popular. But anyway, okay. I think there's one more example. Okay, here, this is how to make 4 different output ports, 4 different 8-bit output ports. And so I use that first shift register here, but I kind of generalized it a little bit, and I guess maybe just a little generalized. Here, first I have a 2 to 4 decode. That's what I've added in here. And what I've got also is these 2 bits here. Consider this, you're going to put the address of the port that you want to output to. The address of the port. And this has nothing to do with the address bus. These are just 2 GPIO pins that you'll put the address. So let's say that here I have a 1 and a 0. I want to output to port 2. Okay. So first there's this thing called Strobe. Let's go straight to the enable of the decoder. If this is high, or 1, or in microprocessors, we just call that a 1. If that's high, then all of these guys are false. The outputs of the decoder are all false if the enable is false. Okay, so all of these clock signals are sitting right now at high. Okay, decide which port. So 1, 0 is my port. So I put a 1, 0 here and nothing happens because this is disabled. But now I set up the SPI for the right phase and polarity, again, rising edge triggered clocks. Write some data to the data register of SPI. And that data is going to actually go into each of these, because the shift clocks are all coming from the serial clock on the microprocessor. And so every one of these parts are going to get data shifted into it. But remember, this guy's high, this guy's 1, 0. Well, once all that data is done, being shifted into these shift registers, all I got to do is make this guy go to low, then high. And when that goes low, this guy is true, and then this one right here goes true. And so it went from low to high, which gave that latch clock, which means all of these things right here are now at those pins. And then we make it go. So it went from low to high, and now it's high, and so we're ready for the next time. Because it's going low that, going from the low to high that made this thing happen. So we went from high to low to high, and that gave the edge we needed. Okay, and so you can write to any of these boards. And this was an old question back in the olden days when I gave really hard exams. I explained how these shift registers worked. And I said, okay, write a program to output a 37 to port 2, the hex 37 to port 2. And so they had to configure the master to do this. They understood, anyway, this was an old exam question. Back in the days that I wanted exams to have averages of, 50, 60. Okay, so that's the lecture. And now I want to give you some example code for your X Mega. Let me open up Atmel Studio, change the screen share. Move the pictures of you all so I can see my screen. Okay, so what I've got up here is the example. We're backing up. We're shifting from port C's master to port D as a slave. That's our goal ultimately. So what I've got here, and I'm not going to write this program. I'm going to step through it and show you the pieces because it just take too long to write it. But we'll keep looking things up as we're doing it. So this is the first thing. I'm just going to swap 1 byte. This is the master's code. I'm going to write 1 byte to the MOSI register master output. I'm going to save 1 byte to the data register of the master, which will send it out. And then I'm going to write the slave code that's going to read that data and at the same time send out some new data. Okay, so master data that I'm sending out is a 1, 1 here. It could be whatever you want. It could be 37, whatever. It's 1, 1. And then here, the data that's going to come into the master, I'm going to store it. I'm going to remember what that is. So that's all. We're just going to exchange a byte between 2 SPIs. And in this example, they'll be the same on the same processor for C and D, but anyway, it doesn't matter. It could be 2 different processors. Okay, so that's the data that I'm going to send out and the place for the data that comes in. So the normal orgs and stack pointer initialization. And then here, let's look at the initialization for the master. Okay, so we're going to want to do least significant bit first, mode 3, and the fastest speed, which is, well, no, not the fastest speed, almost the fastest speed. Divide by 4 instead of divide by 2, which is the fastest. Now, what I've got open here is the include file. And so as much as possible, what we're going to try to do is use the group configurations and the bit positions, bit masks. And so that's why I've got this open. And I've also, I think, here, there. Let me move this up. I've also got the 8331 manual. We're going to be jumping back and forth to this. Okay. Okay, so first thing, which bits are which? Got to figure out which bits are which, and that's a manual I don't have open, so let me open it now. 8385. Oh, by the way, last night there were a lot of problems people having problems with looking at PDF files. And if you use the same technique you use in your lab quiz, those should have opened fine. If you'd have used the internal links, the external links, they should have worked fine. It's when you tried to open it some other way and maybe wanted to use Chrome that it got a little screwed up. But anyway, this is called alternate pin functions. And I believe Chris and Wes showed you this last night. But let's find port C is what I wanted to use. And so port C, you can see right here, slave select is port C pin 4, 5 is MOSI, then MISO, then clock. And you can see they're exactly the same on all the ports. 4 is slave select, 5 is MOSI, then MISO, then clock. Okay, where is that? Okay. Okay, so we're going to set, this is the master. And so I'm trying to set data direction. And so again, and I can't write on this screen anymore, so it's a little pain, but so what do we want the outputs to be for the master? We want it to be that. We want it to be that. And make the slave selected output too, just so you're not, no issues with the pin might go low. And so those are the 3 pins that we want to be outputs. So dir set makes them outputs. And then this is MISO. So we want that to be an input. Okay. Okay, then let's look at the other document. And let me go to that page right there. Okay, so prescaler and clock times 2. So let's go down right here. I want the clock divided by 4, which means I need the clock times 2 to be a 0, and I need the prescaler to be a 0. So they're all zeros. Okay, and so that's called clock period divided by 4. And let's go back here. Somewhere there's a clock period divided by 4. Right there. It says right here, clock divided by 4. So I use the group configuration. Okay, let's back up the page. Then enable. Well, you need to turn on the SPI system. So that's called SPI Enable. So that is not here. It's going to be a bit mask. SPI Enable right there. Now, make sure you don't use bit position for this. That won't work. Right? There's other instructions that we use bit positions. Usually, skip if bits use bit positions. Bit masks are for setting values in particular registers. Okay, let's go back here. DORD, we want this to be least significant bit first. So we need this, let's see, DORD, let's find where that is defined. DORD, if we have, when it's a 1, least significant bit first. So bit mask there. Master, bit mask there. And then mode, let's go back here. There's the modes here, the 3 modes, 4 modes. And we wanted mode 3, so boom, group configuration for that. So, you can write values of 1s, 0s, and all that, but you can also use these group configurations. And what that's good for is then it's really clear somebody doesn't have to look things up to understand your code. And that might be you on a practical. Like last night, right? Some of you used bit values for everything, and you wanted to make a little change, and you had to look up everything. Now, some of you used group configurations, and you could just change the group configuration in the step. Anyway, it's going to be even, when we get to C, we're going to require you to use these group configuration things, because the file name, the completion, the autocomplete stuff, will have all of them built in. Okay, so that's saving it to control register. Okay, now I'm not going to use interrupts in this example, and so you could just leave it the default, but it's always safer to make things that you want to be 0, 0 and not have to depend on your code is running fresh. Some other code hadn't run before. So I'm just turning off the interrupt system, so interrupt control. So I used all of the registers that, the data direction stuff, the control register, and the interrupt control for the SPI. Okay, so that was the initialization. And now, because I've got some data I want to send out, I got to point to that data, which is in program memory. So I use Z to point to that data, and then I just store it into the data register. Store it in the data register, that's it. Process starts. The clock starts running, the data starts going out, and then you can have an interrupt routine, but I don't in this case. Instead of having an interrupt service routine, I just polled. So I have that same kind of instructions that you probably ran for your timer, your first time you did the timer. And so here I'm looking at the status register. And if that one bit, now I'm using bit position, the status is, the status register for this interrupt flag is bit 7, I believe. I looking for bit 7 to be true. And if it is true, then I get out of the loop. If it isn't true, I keep waiting for it to be true. And you might think doing this is going to, if you're running this really fast, then it might be just as fast. If this was running, let's say, at the fastest speed, this might be just about as fast as it takes to get into an interrupt service routine. If you're running this at divide by 128, this takes a lot longer. But you get it. You know how to use interrupt, so you can. Okay, then you got to clear the flag. Now the question is, how do you clear the flag? Well, if you've read the manual, or I think maybe Wes talked about this last night, this flag is cleared a little differently than some other systems. I think you can still write a 1 to the bit to clear it, but I can't confirm because the manuals don't say it. So let's say that that's not the case. So to clear the flag, what it says is you read the status register and then do something with the data register. And so, well, I've already read the status register. By the time I get ready to clear the flag, I've already read the status register, and the operation that you need to do anyway to get the data that came in from the MISO is to read the data register. So by reading the status register here and now reading the data register, that's going to clear the flag. So it's what I call clearing by what comes naturally. So it's not really anything extra you had to do. Now, what if the master input you didn't care about? If you don't care about the master input, the master input, you still got to read it to clear the flag. Okay. Okay. So that is stored in master in, and that's it. And it runs. Boom. And this one compiled okay when I compiled it last night. So let's just trust it. So now I'm going to open another version. And what I'm going to do now is this is the slave. Instead of port C, it's now port D. The master was port C. But other than that, it's going to be very similar. So here, this is the data I want to send out from the slave. I got slave in. That's where I'm going to store the data that comes in. Here I'm pointing to the data I want the slave to send out. And then I store that data to the data register. But this doesn't make anything happen. If the slave is ready, the slave might be ready, 2 days before the master is ready. Not until the master's data register is stored to does anything happen. So I'm in this polling loop maybe for days. It's just waiting. It's waiting basically for the clock to start the whole process. Once the clock starts, it's going to be 8 clock times before it's done. But you might be in here before the clocks are even started. This is fundamentally the biggest difference between the way this kind of system works and asynchronous works. Asynchronous works when you send something, it goes out. When you receive, it doesn't wait for anything. Okay, this is what I had before, which was the way that you clear things by writing a 1, which doesn't work. I'll leave that there. This is writing a 1 to that bit, which again, I don't think works with this processor. A lot of other processors, this will work. So how am I going to clear the flag here? Again, I've already read the status bit. And so I just, again, read the data bit, clears the flag. So this is kind of the old way. Let me get rid of this, I guess, because I don't think that works anymore, which is why I kind of commented that out. Okay, and then that's it. We're done. We got the new data that came in from the slave. So now let's write one program that has the master and slave, one processor that has both. So this is a port. This is going to have port C as the master and port D as the slave, and they're going to exchange 1 byte. So you can actually build this on your board, and this will work. You just have to wire up MOSI to MOSI, MISO to MISO, and serial clock to the serial clock, and ground slave select on the slave. Okay, so I have the same master output and slave output at 4. Got a place for the master input and the slave input. Initialize the master and the slave exactly like I did before, nothing's different. Put the slave output first in the data register for the slave, which is port D, right? Because you got to do that first, because as soon as you do put data in the data register for the master, it's going to start the process. So you got to do the slaves first. Then I point to the master's data and store that in the data register, and the serial communication starts, going from one port to the other on the same chip. Again, you wait, and you can wait on either status registers, either port C or port D. The masters or the slaves, doesn't matter, because they'll happen at the same time. You're waiting for that flag to be set. And when it is set, again, that's the old way to do it. This is what I just wrote some of this last night. So this is how you clear it. Well, we've already read the status register in port C, read the data register in port C. It then cleared the flag in port C, in SPI for port C. Now I got to do the same thing for the slave. Well, in the slave, I didn't read the slave status register. So I got to read the status register, even though I don't care, because I know that bit is set, but that's how you clear the flag. And then the data that the slave got in, well, I need to read it anyway. So let's just read it. And so I had one extra instruction that you wouldn't need if you just write a 1 to that flag. Okay. Now I could run this code again. If I just took my processor and wired things up, I can run it, but I'm not gonna. But in theory, I could. I just didn't do it last night. I'm not going to show you today. Okay. One more thing I want to do is show you how to change this. Instead of swapping a single byte, now I'm going to have a table of bytes. So this is more likely something you would do. This would be some kind of dynamic thing. There's a table, and every so often you got to take a whole table, send it from one device to another. But because we have a master and slave talking to each other, I'm going to send out a whole table from the master, and I'm going to receive a table from the slave. And so I just got a bunch of numbers. We saw this in the table load example at the beginning. Add those numbers up, it turns out to be 37. But that's not what we care about here. So there's a table full of numbers. And if you haven't seen this trick before, this was in some of I think I showed this in some code before, but n table minus table, where n table is just the label for the next line. Remember that tables in program memory have 2 bytes each. So that would be 1 address, 2 address, 3 address, 4 address, 5 addresses. So n table minus table would be 5. And say multiply by 2 because I know there's 2 bytes per address. So this is a way to know how big your table is without having an equate that says count those values, table equals 10. This is a way, that way, if I just added more values here, it automatically would calculate the new table size. Anyway, it's something that probably useful to know. Okay, and so now I've got to define a table for the inputs that are going to come to the master, a whole table full of inputs, same size as this table. And we're just going to see what's different of this program and the other program. Well, we're going to initialize the master just the same. The only thing different now is I've got to have some kind of variable for the table size itself. So I put that in R17. I point to the beginning of the table with Z, which is what I have to do for program memory. I use X or Y, in this case X, to point to where I want to put the table that comes in. And I store the data, the first byte in the table, to the data register. Starts the process. Notice I increment Z on the process. I have my same wait for that 1 byte to be sent out. When it is sent out, then when it's all sent out, then I can read the data in the data register. Again, this clears the flag because I read the status register, and read the data register. And so the data that came in, I'm going to store that where X points. That's the slaves table. And again, increment X. Then I want to make sure, hey, am I done? Well, this was just the first of my 10. So I'm decrementing 10 to 9. 9 is not equal to 0. And so I loop the whole thing again. So this will run 10 times to exchange all 10 bytes of data. And that's it. And one more program I want to show you, which is, again, very similar. This is swapping bytes from the slave's point of view. And so again, I have a slave table, and I made the values different so you could see those easy. If you actually ran this, still got that table size thing. Now a place to store the inputs that come from the master's output, slave input table. Everything else is exactly the same. Here I'm pointing to the slaves table with Z because it's in program memory. I'm using X for the master's, the table, the inputs that come from the master. And then this loop is almost identical, except, let's see, so we store data to the data register. Again, that doesn't start anything until the master's got some data in its data register. And when it does, we run through this loop. When that loop is done, again, let's get rid of that. When that loop is done, there's some data available. Well, I've already read the status register. Hold on here. This is some mistakes. I see some mistakes here. This should be port D. Okay, so port D, I'm waiting for port D to be done. When it's done, then I read the data there, and reading the data because I saw that flag of the status register and the data register, I cleared the flag. Store this in the table I've set up, and then again do this 16 times. Oops, so that should be a D also right there. Okay. And that's it. And so now, again, I could run this, I could write some code that does swapping of bytes, but it turns out with only 3 pointers, a Z and an X and a Y, I'm short a pointer. And so I have to do these kind of kludgy stuff, which I don't think is worth, it doesn't help us understand. So I didn't do the next step. I did it with, I've done this same kind of program with the last 3 processors we used. All had different ways to do things with pointers that our processor doesn't have. It's not hard to do, but I just haven't done that last step. Okay, so that's how SPI works. So let's open the lab. Oh no, I can't open it because it's not yet posted. So let me talk a little bit about the lab. So with this lab, you're going to interface with an IMU, Inertial Measurement Unit. The IMU has 3 accelerometers and 3 gyros. Solid state, we call them. There's no real gyroscopes on it. It's what's called a solid state gyro. And what you have to do in the lab is you have to interface with the accelerometers on the IMU. What you can do then is you can know if your board is level, because basically what's going to show you is how it accelerates. And if you've had physics, you know that acceleration due to gravity looks just like acceleration. And so if the board is like this, there's going to be a vector pointing to the gravity acceleration down. And if it's just sitting on a table and the table's not moving, accelerations in this direction and this direction will be 0. So you can know if your table is level. Right? In fact, you can use this lab to see if you hanging your pictures properly, if your pictures are level on the wall, your paintings. In fact, that was one of the, we did this in one of the practicals a couple of years ago, second practical. We had the students make a level. And then this was when we were live, and the pies went around and they put something there, and they had like a something that was 45 degrees and 30 degrees. And we could see if they did it right. Okay, so that's what you're going to do. So to do this, you're going to have to learn a little bit about this IMU. And the document for that IMU is on our website already. So let me show you that. And the document will be posted, if not today, tomorrow for sure. Right here. Except since COVID happened, you know, there's chips are hard to get. Lots of chips are hard to get. If you can find buy a new computer chip, it may cost you a lot more than it did before. But also IMUs are now really hard to get. And so since COVID happened, we've had to switch 3 different times for 3 different IMUs. And in fact, the guy who makes our boards is telling me that he doesn't know if he can get them at all starting in the fall. And so we're going to probably in the fall start using 2 microphones instead of an IMU, which is a little bit of a pain, but until the chips come back, we're going to do that. Anyway, there's the spec on an IMU. This may not be the exact one you have, but I'm pretty sure that the 2 IMUs that some of you will have different ones, they'll be pin compatible. They'll work exactly the same. They'll be slightly different spec sheets. Think the same company. But anyway, that's the Pi is verifying all that today. That's why the lab isn't yet available. But this document will explain a little bit about this. So this is an external device that they'll be control registers you're going to write to. Just like inside your processor, they're control registers, except we're not connecting this with the EBI system. So we're going to write the control registers by sending an address from your microprocessor is going to be a master. So you're going to send an address of the control register, and then you're going to send the data to that control register. And once you have it all set up, then you're going to read the data, and the data will be the X and the Y and the Z acceleration. And you'll display this somehow. Probably, I think we have you using your UART to display those values. And then we actually have you plot. There's a program that we have called Serial Plot. And there may be a newer version of this, but this is the one we used last semester. Serial Plot allows you to do plots, real-time plots. So we'll take the information of the IMU, the accelerations, and do 3 plots on the same graph and see how, you can put this in your car and drive real fast and then stop and see what the acceleration is. Don't do that and get in an accident and blame me. But anyway, you can then do it. See what happens if you drop your board and it smashes on the table. What's the acceleration? Again, don't do that. You might break it, but you might move it real fast. Just make sure you don't move it so fast that the cord takes your computer flying across the room. But anyway, there's some fun things you can do with this. And I think there's a little bit extra credit that we have if you also do the gyro. If you also get the gyro to work, just a couple points of extra credit. It should be pretty straightforward. It's just a couple more configuration registers that you'll have to set up and read. Okay, so if you want to learn about a lot of this is again from last semester, but all but this document are probably here and they're not going to change much. But if you're looking for something to do, maybe you've already done your lab 5, then you got something you can work on.